Okay, ji, Bismillah Rahman Rahim. Today we'll be beginning the discussion and the revision of Unit 7 in preparation for your IGCSE O levels Paper 1 exam for your May-June 2022 exam. So if the agenda is that, first of all, we'll cover the entire syllabus for chapter 7, and hopefully we'll have enough time to go through a few questions as well, and then that will conclude our revision for chapter 7. Okay, first of all, let's go through the introduction of chapter 7. The basic focus of chapter 7 is the discussion between your language translators. So basically what a language translator is, that in computing terms, we are giving our computers instructions. Okay, our computers are basically instructions executing machines. So as we have learned from the von Neumann architecture, all computers are simply executing instructions in sequence. Where do those instructions come from? They come from us, obviously. So whatever task we want the computer to perform, we give those give those tasks as a series of instructions, and our program counter simply increments the address, and that address is linked to where the instruction is in the memory, and automatically the instruction is being fetched, execute, decoded, and executed. This is what we studied in chapter 4. Now, basically, we're going to be looking at what different methods have existed or do exist right now for us to write these instructions. Originally, we wrote code in machine code, right? Now, what machine code basically is, it is a sequence of ones and zeros, and this is how we used to give our instructions to computers. Now, if we look at machine code, it is a simple, steady stream of ones and zeros. It's very difficult for us to write, very difficult for us to understand. For a machine, for a computer, it is their native language. It is what they understand. They are very, quick in responding to ones and zeros, because their fundamental architectures are logic gates, and logic gates are switches that are either on or off. Therefore, they are very easily understanding the ones and zeros. But the thing is, it becomes very difficult for us to write this. But regardless of which, this machine code, let's just say that this particular, instruction has two parts. You can say that all instructions are made up of two parts. There is the opcode and the operand. So basically, opcode refers to as what the instruction requires it to be done, and operand is what data will be used for the instruction to be executed. So these two parts are somewhere divided in this instruction. But the reason I'm saying somewhere is that different computer architectures have different processor families, have different formats. Some say that, let's say, for example, we have the first 8 bits for the opcode and the remaining for the operand. Some will have other divisions, but regardless of which, most instructions are divided into the opcode and operand format. And this is how our machine basically understands what is to be done and what data is to be used while instruction is to be carried out. Now, as you can see here, these ones and zeros, these instructions are not easy for us to understand. They are very easy for the computer to understand, but not for us. They are difficult for us to write. They're difficult for us to read, understand, and more importantly, they are very difficult for us to debug in the event of some sort of error. So we had to think of some way to make improvement and make the effort of coding easier. And this is where the concept of low-level programming languages came in. Now, low-level programming language means that it is code that is near machine understanding. Now, one thing I need to make clear is that just because it's near machine understanding, it is not machine understanding. So do not confuse low-level programming as machine code. They're two separate things. And even if you do write something in machine code, it too has to be translated into your, sorry, if you do write something in low-level programming, it too has to be translated into machine code for the machine to be understanding it. So, but since it resembles somewhat a machine code format, it is known to be, it is said to be near machine understanding. Regardless of which, it makes use of mnemonics. Mnemonics are small words. So for example, if I have something, an instruction is like add hash 40, or for example, I will just say add, yeah, add or add 100. Now what this does is that this instruction, as you can see here, this is one line of an assembly language code. Assembly language is, as you know, a low-level programming language. This corresponds to, this is an example of assembly language code. Now what this does is that it adds, now as you can see here, this word here, this is what a mnemonic is. If I look at this word, it makes some sense to me. So it is, you know, understandable by me, but yet what this 100 means is that it is actually an address in my memory location from where I want to load some data and I want to add the contents of which to the ACC. Now, this is not apparent from this instruction, but yet it is what it means. So 100, I can't really exactly tell what 100 is. I mean, if I did not say there was an address, you would not have known. You might have thought that it was just a value that's being added to some place. Now, this is why it is not that much understandable by humans, but because of these words, these mnemonics, it's easier to understand and easier to write. But still, it is closer to machine code, right? Okay. Anyway, then finally we have the high-level programming languages. These are near human understanding. Now, what does that mean is that they make use of natural language words as instructions. For example, I will write an instruction something like this: inputs, enter a number. Now, say for example, this is some high-level language, which it isn't, it is pseudocode, but let's just say, for example, it's a high-level language. I can very easily say that what it's asking me to do is that it's asking me to enter a number, and a user will give an input. These codes will be presented on the screen. Whatever the user will give as an input will be assigned to this identifier. So now that is very easy to understand. Similarly, if I write some arithmetic operation, say for example, I say B is equal to A plus C. Now, as you can see here, it is resembling very much like our normal arithmetic operations. I have a variable A, the contents of which will be added to variable C, the result of which will be stored in B. Now, if I were to tell you that this is what Python does, you'll be amazed that this is actually what Python syntax does. And Python, in this sense, is very much similar to your arithmetic operation that you do in your everyday lives. So this is why high-level language are considered as near human understanding, because this syntax resembles what we would have done in our natural languages. Now, the thing is, high-level languages are easier for us to understand. Their code is shorter. It is easier to code. It's easier to debug. But the problem is that since they are aware, they're more away from, they're further away from the machine code, they will have to do a lot more complex translation to end up in machine code. Now, to summarize this section, I will have to make one thing clear. First of all, machine code is all ones and zeros. This is it. This is what the computer understands in its raw form, right? Everything that is written to every data, every instruction that is given to the computer is written in this form. Now, we used to write instructions in this form, but that was difficult. Then and as you can see here, it's very difficult to understand, difficult to write, difficult to debug. Then further improvement came when we started working on low-level programming language. Now, low-level programming language means that it is not actually machine code; it is near machine understanding. And in a sense, it's easier for us to understand because it makes use of small words such as mnemonics, like this one right here. So, for example, we written here instruction add 100. This is a mnemonic. Now, I can very clearly tell you what add means because that's the word that we use in our real life as well. For example, there's another one like this. So as you can see here, SUB, of course, that means sub. And possibly you can make something out here, JMP, and possibly maybe it means jump, which it does mean jump. So as you can see here, these mnemonics, they somewhat give an ease for us humans to make a write code or understand code what's happening here. But the thing is, it is not machine code. Low-level programming, even if it is easier, it is near machine understanding, it is not machine code by default. It too requires translation. Finally, if we come at high-level programming languages, high-level programming language make use of syntax that's closer towards human understanding. Now it is closer to human natural understanding, human natural way of doing things. So for example, I have done one instruction here that adds two values, the contents of two variables, and stores the result in the third variable. Now this is what we would have done in normal algebra and any other arithmetic operations. So you can say here that this is exactly the same way that we do in a natural state. So that's why you can say that high-level languages are near human understanding. Now, finally, if it's low level, I will repeat this one last time because I see a lot of students confusing machine code with low-level programming. Now, you repeat this one last time. If you're writing high-level language code and you want it to run, it will have to be translated into machine code. So this is not understandable by the computer. It will have to be first translated into this version, then the computer will understand it. Similarly, if we are writing in low-level programming code, so for example, I wrote this line, this is not right away understandable by the computer. It too will have to be translated into machine code. Only machine code is by default understandable by the computer. Okay. Okay. So this is the basic introduction of machine code, low level and high level. Now let's look at some more details of low level programming languages. Now I have already mentioned that your machine code is a division of two parts, opcode and operand. It's all basically ones and zeros. The opcode and operand number of bits are decided upon based on the processor family. Each processor has its own instruction format. That's a complete separate thing. That's not a part of your syllabus. You don't have to worry about it right now. But basically, it's all written in machine code, all in ones and zeros. However, if you come to low-level programming language, now this is interesting. If I say, for example, write an instruction like this. Now, LDD means load using direct addressing. This is the code that is used very commonly in assembly language. And it's basically telling me to load something from this address and store it in a general purpose register known as the accumulator register. Now, whatever it does, this is a commonly used instruction in assembly language. As you can see here, it makes use of what we just discussed a little while ago, the mnemonics. That's exactly what it's doing. So the thing is, this is not right away understandable by the computer. And when I run it, it will use a translating program. We'll be discussing that in a bit. It will use a translation program to convert this assembly language code into machine code. Okay, now the thing is, since this assembly language code is near machine understanding, that means that it is almost, somewhat like machine code. It is not machine code. It is almost like machine code. And that's why when I want to eventually translate this into machine code, the effort will not be that much. The translation process will not be that complicated. And that's why the translation software that will be used to translate this code into machine code, it's not necessarily a complicated software. By the way, that is true. If this is assembly language code, we use a translation software known as assembler to convert this software into its destined machine code. And assemblers are not that complicated. They operate in two passes, and they basically perform this translation process in two steps. Now, if this one single line, now this is very important to know here, if one single line assembly language is written or low-level programming language is written, it will translate into only one corresponding binary line, machine code line. So what it means is that each line in assembly language code translates into only one line in machine code. So for example, let's say that this just for example, this first 1, 2, 3, 4, 5, 6, 7, 8. First 8 bits represent this thing, and the remaining bits, whatever they are, they represent the opcode. So if, say, for example, I have this LDD1, I mean, don't worry about this not being 100. It's just an example. I'm just saying an example. Let's say, for example, that LDD is represented by the 4 most significant 8 bits, the left side 8 bits, by this LDD is translated into this, and the remaining bits are used to translate this. So what happened here is that only one line, one assembly code line, when translated in machine code, only results into one machine code line. So as you can see here, it's always a one-to-one relationship. One line assembly language results in one line machine code. So actually, very relatively simple to translate. If you look at it, all I need to know what the binary code for LDD is, and I simply replace that binary code of LDD. I replace the LDD with the binary code that represents LDD. Similarly, I replace the binary code for 100 in the operand portion, and there you go. I have the machine code instruction. So the translation process is relatively simple, and each line in assembly language code will result in only one line in machine code, right? Now, another thing is that if you look at high-level languages, say for example, I'm doing something like this: A is equal to B plus C. Now, this is apparently this looks like a single line to me, but if I were to convert this into machine code, this would result in possibly 2 or 3 lines. So for example, if I would write this exact same code in assembly language code, it would look something like this: LDD B add C STOA. Now, this one line in assembly language, one line in high-level language results in 3 lines in assembly language code. And this code exactly represents what's happening over here. Now, if one high-level language code results in 3 assembly language codes, that means if we have one-to-one relationship between assembly language and machine code, this would also mean that this results in 3 machine language codes. So we can say that the translation process for a high-level to machine code instruction, as you can see here, this will result in its own binary code, and this will result in its own binary code. And this will result in its own binary sequence, like so. Now, as you can see here, the translation process of a high-level language code may result into multiple machine language codes. Similarly, the translation of one low-level language code will result in only one machine language code. So this is what we need to understand over here, that all languages are translated into machine code. However, the translation process for your low-level language is slightly difficult as compared to, the translation process for your high-level language to machine code is slightly complicated, whereas the translation process from your low-level to machine code is relatively simple and straightforward. You're converting one low-level language code into one machine level language code, whereas you're converting one high-level language code into possible multiple machine language instructions. So this is the basics of our low-level, high-level languages. And now let's look at the differences between our language translators, namely the assembler, compiler, and interpreter. Okay, now basically what the purpose of language translator is that, as I mentioned before, that all source code must be converted to machine code. So may it be assembly language, may it be high-level language, it all has to be converted to machine code. So whatever you do, the end result is machine code. So therefore, you will always need some sort of language translator to convert to machine code. Now we'll be looking at three types of language translators today, and this is basically the most important part of your syllabus so far. Right? Okay, the first type is known as assembler. Right now, assembler. Let's look at the features of assembler. First of all, it is used for converting low-level language to machine code. Oh, by the way, I'm going to pause it right here. I forgot to mention some examples of high-level languages. You know the as an example of low-level language is assembly language. Now, for example, high-level languages, one possible example could be your what you call it, Python, and then we have Visual Basic, Java, C#, C++, so on so forth. One other thing that I forgot to mention here is that low-level programming languages are machine dependent. Now, what that means is that machine dependence means that one type of processor family, one processor family, let's rephrase it, assembly language syntax for one processor may differ from another processor family. So for example, if we have two processor families, say Intel x86 and I have another processor family, say ARM, they both will have assembly language syntax that's different. So I cannot simply use the same assembly language code or the same way of writing assembly language code for both types of processor families. So this is what it means by machine dependency. So I cannot simply translate one assembly language syntax to another, from one processor family to another without any problem. Now, different assembly language codes differ for different processor families. When you guys will be, going in A levels, we'll be looking at this syntax right here, and this syntax resembles the little man computer syntax, and that's a different type of processor altogether. So this is what it means by machine dependence, that this assembly language code varies for one processor family to another processor family. However, if we look at your and also one more thing, that if you look at this fact, that when an assembly programmer is working on a assembly code, then they will require knowledge of the underlying hardware So if they have no idea what processor they're working on, they might end up writing the wrong assembly language syntax. So that's why when you're working on a machine dependent language, underlying architecture has to be made part of your knowledge. You have to know what you're working on, or you have to know what machine the assembly language code will be working on. You have to adjust your code according to the underlying architecture. So this is what it means for something to be machine dependent. Finally, let's talk about high-level languages. Now, high-level languages are machine independent. This means that the code written, the coder does not have to have previous knowledge of the underlying architecture. So what that means is Python code is the same for all types of computers. Whether you're writing Python code on a smartphone, on your desktop, on a Mac OS, or Intel M1 process, or sorry, Apple M1 processors, the syntax does not change. So this is what it means by machine independent. You can simply use the same syntax for the same language on any architecture you're working with. So this is one of the added benefits of working for your high-level languages, right? Now, I'm going to pause this video over here, and we're going to continue with the discussion of or differences between language translators, assembler, compiler, and interpreter, and then we'll look at the different types of errors, and finally the role of the